Hello everyone, welcome again to our YouTube channel Engineers World. So in the previous lecture we studied about different types of modulus of elasticity of concrete. We studied the stress strain relationship of steel also, and we started with working stress method. Now in today's lecture I will again start with stress strain curve of HYSD bars, cold worked HYSD bars, because we have to discuss one more thing here. So the stress strain curve of HYSD bars was like this, where it showed no specific yield point. So we assumed that as per IS 456 that it showed yielding at 0.2% of strain. That point comes to be like this. 0.2% means 0.002. And this strain is called plastic strain. Now, if we see the point corresponding to the peak of this curve on the x-axis, this point will show the elastic strain recovered. And its value is given as Fy upon Es, where Fy is the yield strength of steel HYSD bars and Es is the modulus of elasticity of steel. See, Es, the value of Es we take as 2 into 10 to the power 5 Newton per mm square. And Es will be Fy upon elastic strain. So from here elastic strain will be, do you know how this came? Because Es, we know that modulus of elasticity is stress upon strain. So here it is yield stress and strain is elastic strain. So see, this is stress and this axis shows strain. This stress is at this elastic strain. The stress is Fy. So elastic strain we get as Fy upon Es. So this is our elastic strain. Now coming to the total strain. Total strain at yield will be, everyone of you can say what will be the total strain at yield limit. So total strain at yield limit will be simply 0.002, this plastic strain plus elastic strain plus Fy upon Es. So this term represents the total strain at yield limit. So this was a further explanation of the stress strain curve of cold work HYSD bars. Now we will again move to working stress method, which we started in the previous lecture. So in the previous lecture we studied what the working stress method is. So I'll again briefly discuss some of the important points here. The first is, working stress method is based on actual stresses developed due to actual working loads. Actual stress developed due to actual. So our working stress method is based on actual stresses developed due to actual working loads. Actual stresses developed due to actual working loads. Secondly, stresses developed are kept within permissible stress values. Within permissible stress values. And third point here is the permissible stress is given as characteristic strength upon factor of safety. If I write permissible stress, it is simply given as characteristic strength. That may be FCK for concrete or Fy for steel upon factor of safety. So this is the important point. Next, and the most important point, is factor of safety is applied to stress values only. Factor of safety is applied to stress values only. Remember, in WSM, the factor of safety is applied to stress values only. And the structure is designed for actual working load without applying any factor of safety to load. So there is no factor of safety is applied to load. That means our load factor of safety is 1. Load factor of safety is simply taken as 1. So these were some of the important points for working stress method. Now we will move to factors of safety in working stress method. So, factors of safety in working stress method. So you need to remember these some of the values. First one is stress factor of safety for concrete. Stress factor of safety for concrete, it is taken as 3. Remember. Second is stress factor of safety for steel. Stress factor of safety for steel in case of WSM is taken as 1.8. These values need to be remembered. Load factor of safety for both steel and concrete is 1 simply. Load factor of safety for both concrete and steel, we take it as 1. So this was all about the factors of safety in case of WSM. Now we will move on to the various assumptions in the working stress method. So what are the various assumptions in case of working stress method? So starting with the first assumption. The first assumption is at any section a plane section before bending remains plane after bending. At any section a plane section before bending remains plane after bending. Remains plane after bending. Now, what does this assumption mean? The meaning of this assumption is that the strain diagram is linear for all sections subjected to bending. See, when a beam bends due to any moment or any other reason, strain values at every points are proportional to the distance of the points from neutral axis. If this is the beam subjected to any loading, this is our neutral axis, and these are two sections. This is 1, and let this section be 2. This is the cross section of beam. This is our neutral axis. This is some tensile steel. So this shows a straight line. That is our strain diagram. This is our strain diagram. See, at distance y1 from the neutral axis, our strain comes to be epsilon 1, and at a distance y2 from neutral axis, below the neutral axis, our strain value comes to be epsilon 2. So this epsilon 1 is directly proportional to y1 and epsilon 2 is directly proportional to y2. So this is the meaning of the first assumption, that is at any section, a plane section before bending remains plane after bending. Now moving on to the second assumption. So our second assumption says that all tensile stresses are taken by steel only and none by concrete. All tensile stresses are taken by steel only and none by concrete. Now what does this mean? Concrete, see, we know that concrete has very low tensile strength. For analysis, concrete sections on tension side is completely neglected. So this statement is valid for only cracked section. So based on stresses developed in concrete, the section may be considered as cracked section or uncracked. So there are two sections, one is cracked and another is uncracked. So what is uncracked section? In case of uncracked section, or if FCT is less than or FCR. And what is FCR? FCR is modulus of rupture, that is equal to 0.7 root FCK. So in this case, concrete will not crack. And what is our FCT? FCT is our tensile stress. So in this case, the tensile stresses are considered taken by steel and concrete both. Concrete section in tension zone is not neglected, and total area of concrete is considered in analysis. So if we go for the next, that is our assumption. So next assumption says that stress-strain relationship of steel and concrete under working loads is a straight line. The stress-strain relationship of steel and concrete under working loads is a straight line. So if I draw the stress strain curve of concrete, it is somewhat like this for concrete. So see, this portion is a straight line. This is stress versus strain. So these are the corresponding points. This is our characteristic strength of concrete, and the corresponding strains are, these are 0.0035 and here it is 0.002. So this is a stress strain curve for concrete. Now stress strain curve for steel I already explained you, but I'll still draw it here. Somewhat like this. And here it is 0.002. This is a straight line. This peak shows our Fy. So this was all about the third assumption. Now moving on to the fourth assumption. So what is the fourth assumption? The fourth assumption says about the value of modular ratio. The value of modular ratio. See, I have not discussed about this modular ratio. The modular ratio is denoted by small m, and its value is the ratio of Young's modulus of velocity of steel to the Young's modulus of velocity of concrete. That is ES upon EC. But as per IS 456, its formula is 280 by 3 sigma CBC, where I have told you what sigma CBC is. Sigma CBC is simply combined effect of bending, compression and tension. That is bending stress. Permissible bending stress. What is this? Permissible value of bending stress. So this is all about modular ratio. Now see the use of IS 456 provides us a table in which we have sigma CBC values for different grades of concrete. So this is the table where it shows grade, and these are sigma CBC values. For M15, sigma CBC value is 5. For M20, sigma CBC is 7 Newton per mm square. And for M25, its value is 8.5 Newton per mm square. For M30, it is 10. For M35, it is 11.5. For M40, it is 13, and for M45 it is 14.5. So as far 456 provides the values only till M45. Now see, the values of modular ratio M can be calculated as per the above formula, 280 by 3 sigma CBC. See, this formula can further be modified as, if we divide 280 by 3, we will get the value as 93.33 upon sigma CBC. So on substituting these values, we will get the corresponding values of modular ratio as 18.67, 13.33, then 10.98, and then 9.33, 8.12, 7.18, and then 6.44. So this was a table from IS 456. This table will be required while solving the numericals, so you must remember this. Now next we will study the use of this modular ratio. See, its use is very wide, so we will study about the use of modular ratio. I'll simply write it as M. See, in case of composite section, if I talk about composite section, always strain values are same in two materials at a particular location. For example, this is a composite section subjected to a tensile load. For example, this is a section subjected to a tensile load P. These are the reinforcing bars, and this is its cross-sectional view. These are the reinforcing bars. So it becomes a composite section. The area of these steel bars can be denoted by AS, and area of concrete can be denoted by AC. And on this area of steel, force PS is applied, and on this area of concrete, force PC is applied. And the force PS is applied and it gives to stress small ps, and PC leads to the stress small pc. Now, at any location, elongation in steel will be equal to elongation in concrete. We know the formula of elongation, what is PL upon AE. So P steel into L upon area of steel into E steel, Young's modulus of velocity of steel, is equal to this load value in force in concrete into L. Length is same for both the members, of this composite section, upon AC into EC. This L values will be cancelled, and if I take these values here, we will get PS upon AS will be simply stress in steel, PS, and upon ES will be equal to stress in steel upon EC. So PS upon PC is equal to ES upon EC, and we know what is ES upon EC. It is modular ratio. So we can write as stress in steel as M times stress in concrete. So here we can write stress in steel as modular ratio times stress in concrete. So this is an important formula here. T, and stress in concrete is denoted by C. Then we can simply write it as T is equal to M into C, or C is equal to T by M. So these are our two formulas. So moving forward, now if I calculate the total force in this composite section, total force P will be force in steel plus force in concrete, and we know force is stress into area, so stress in steel into area in steel plus stress in concrete into area of concrete. And we can write PS as I wrote here, PS is equal to M times PC. So I can replace it with PC, M into PC into AS plus PC into AC, or I can take PC common. It is M times AS plus AC. So total force is this. See, this portion, this is called as equivalent area in terms of concrete. Equivalent area in terms of concrete. So in this composite section, we have converted the area of steel into equivalent area of concrete. So this is the main function of this modular ratio. See, if I show it by using diagram, I can show it like this. See, if this was our original section in which these were reinforcing bars, or you can say this was our AC, this portion, and this was our area of steel, AS, and if this was our depth, this was width, then we have transformed this area into like this. Where these are hollow. This hole is AC and this is M into AC. M into AS, sorry. So this is the main function of modular ratio. See this area of steel, this steel has got converted into equivalent area of concrete. So if I write the formula of area of concrete can be written as this B into D whole D minus area of steel AS plus M times AS. So this is the equivalent area of steel, or we can further write it as BD plus M minus 1 into AS. So this is our equivalent area of concrete, equivalent. Now see, if I'll also give an example on this so that you can understand it in a better way. See, for example, this is our beam section, cross section. This is our tensile steel. Now, if we have neglected this, so this is simply our AST. If we have considered only concrete above the neutral axis, and we have neglected this portion of concrete. So, if we convert it into equivalent area, so if we convert this AST into equivalent area of concrete, so the new section will be just like this. So this will be M into AST. That is equivalent area of concrete. This will be same or concrete. This is our concrete. This is also concrete. So this is the function of your modulus of modular ratio. Now if this depth is XA, so say here, in this case net area will be equal to B into XA plus M into AST. So this will be the net area in this case. Now this was basically cracked section because we have neglected the concrete on tension side. Now if I take uncracked section, so in case of uncracked section we will see what happens. This is your beam cross section. This is your steel. this is your overall depth D, and if this is your effective depth denoted by small d, and this is the width P. This is your neutral axis. So if I convert it into equivalent concrete, so it will be just like this. So this AST is converted into M into AST. Here again it is your overall depth and this is your width B. So in this case our net area will be BD minus AST plus M times AST. Because in case of uncracked section, here we are considering concrete on tension side. So we are here, why we are negating this minus AST? This minus AST is basically the concrete which will come in this zone of AST. That's why we are subtracting AST here. So A equivalent area will be BD plus M minus 1 AST. Simply. So this was the use of modular ratio, how we can use this modular ratio in cracked as well as uncracked section analysis. Now we will discuss in detail about the stress strain curves for concrete. So if this axis shows strain values and this axis shows stress values, so we know that to enable the mathematical treatment, the stress strain curve is assumed to be a parabola up to a strain of 0. Assumed to be a parabola up to a strain of 0.002 strain. So up to this strain, it is assumed to be a parabola followed by a straight line. See, the actual path that it should follow should be this, but it is actually followed by a straight line. So this is our actual curve. And this will be called as our idealized curve. So corresponding to this value, this will be our sigma max, maximum stress. That will be equal to FCK, that is characteristic strength. Now the maximum, the strain value here is 0.0035. Now Now the effect of size and shape of the test specimen with that of the actual structural member in flexure is taken into consideration, and this idealized stress strain curve for concrete in the member is obtained by multiplying each ordinate by 0.67. So we will multiply each ordinate by 0.67. So corresponding to that, we will get in this case F max will be, or sigma max will be 0.67 times FCK. See, this was FCK. We have multiplied these values with 0.67 FCK. So this gives us idealized stress strain curve for concrete in the member. Now, in addition to this partial safety factor gamma m of 1.5, if we if this partial safety factor of 1.5 is applied to get the design curve, so design stress works out to be. So our design stress now will be 0.67 FCK by 1.5, which will give us 0.446 FCK. So the curve corresponding to this will be just like this. So this represents our design stress denoted by FD. This is equal to 0.446 FCK. So this was all about stress strain curves of concrete. So if we see from here, so this curve is our actual curve, this is our idealized curve for concrete in member, and this will be our design curve. And the stress corresponding to design curve will be 0.446 FCK. Similarly, stress corresponding to the idealized curve for concrete in member, idealized curve for concrete in member is given as 0.67 FCK. So this was all about the idealized stress strain curve. I'll write here idealized stress strain curve of concrete. So this was all about today's lecture. Hope you would have liked the lecture. So if you have liked the lecture, please like the video and subscribe the channel.